Welcome to our exploration of periodic trends, atomic radius, and ionization energy. Why do atoms get larger as we move down a column of the periodic table and smaller as we move across? Why does it take more energy to remove an electron from fluorine than from cesium? In this presentation, we will explore these fundamental patterns that govern chemical behavior across all 118 known elements. Discovered through the pioneering work of Mendeleev and Moseley, these trends allow us to understand and predict chemical bonding, reactivity, and the very structure of matter itself. The Pauling electronegativity scale was introduced by Linus Pauling in 1932. Pauling noticed that the bond between two different atoms is stronger than expected from the average of their homonuclear bonds. He quantified this additional stabilization using bond dissociation energies. On the Pauling scale, fluorine is the most electronegative element with a value of 3.98, while cesium is the least at 0.79. The scale is dimensionless, and the difference in electronegativity between two bonded atoms, when squared, equals the excess bond energy in electron volts. The formula is the absolute difference of chi A minus chi B equals the square root of the dissociation energy of AB minus the average of AA and BB, all in electron volts. Let us visualize the Pauling scale. Here we see elements arranged from left to right according to their electronegativity values. Cesium at 0.79, potassium at 0.82. Sodium at 0.93, and lithium at 0.98 are all low. Hydrogen sits at 2.20, followed by carbon at 2.55, nitrogen at 3.04, oxygen at 3.44, and finally, fluorine at the top with 3.98. The height of each bar represents the electronegativity value. Notice the smooth progression from the electropositive metals on the left to the highly electronegative nonmetals on the right. This ranking directly correlates with each element's position in the periodic table. Robert Mulliken proposed an alternative definition of electronegativity in 1934. Instead of using bond energies, Mulliken defined electronegativity as the arithmetic mean of the first ionization energy and the electron affinity. This is called absolute electronegativity because it is derived from fundamental atomic properties. The formula is chi equals the sum of EI and EA divided by 2. To convert Mulliken values to the familiar Pauling units, we apply a linear transformation. Chi equals 0.187 times the sum of EI and EA, plus 0.17 with energies in electron volts. The Mulliken scale has a clear physical interpretation. It represents the negative of the chemical potential of an electron in the atom. Here, we break down the Mulliken formula visually. On the left is the core equation. Chi equals the average of ionization energy and electron affinity. On the right is the conversion to Pauling units. At the bottom, we see why this matters. The Mulliken scale does not rely on any arbitrary reference point, unlike the Pauling scale, which uses hydrogen as a reference. It is directly derived from two measurable atomic properties, giving it a rigorous physical foundation. Understanding both scales provides deeper insight into atomic behavior and how electronegativity relates to fundamental atomic structure. The electronegativity difference between two bonded atoms determines the type of chemical bond. When the difference is less than 0.4, the bond is nonpolar covalent, meaning electrons are shared equally. Examples include F2 and H2. When the difference is between 0.4 and 1.7, the bond is polar covalent. Electrons are shared unequally, creating a dipole moment with partial positive and negative charges. Water and hydrogen chloride are classic examples. When the difference exceeds 1.7, the bond is predominantly ionic, meaning electrons are transferred completely. Sodium chloride is the textbook example. The greater the electronegativity difference, the more ionic character the bond possesses. This visualization shows the bond type spectrum. At the top, we see the continuum from nonpolar covalent on the left through polar covalent in the middle to ionic on the right. Each column shows a specific molecule: F2 with 0 difference, HCl with a difference of 0.96, HF with 1.78, and NaCl with 2.23. Notice how the bond type changes from nonpolar to very polar covalent to ionic as the electronegativity difference increases. The percentages of ionic character can be calculated using the formula 16 times delta chi plus 3.5 times delta chi squared. Electronegativity follows clear and predictable periodic trends. Across a period from left to right, electronegativity increases. This happens because the nuclear charge increases while the atomic radius decreases, making the nucleus more effective at attracting bonding electrons. Down a group, electronegativity decreases because the atomic radius increases and the valence electrons are farther from the nucleus with more shielding. There are notable exceptions. Gallium and germanium have higher electronegativities than aluminum and silicon due to the d block contraction. The 3d electrons do not shield effectively, making these period 4 elements smaller and more electronegative than expected. Here we see the periodic trends visualized with bar charts. Across period 3, electronegativity rises steadily from sodium at 0.93 through magnesium at 1.31, aluminum at 1.61, silicon at 1.90, phosphorus at 2.19, sulfur at 2.58, and chlorine at 3.6. Down group 17, the halogens, electronegativity falls from fluorine at 3.98 to chlorine at 3.96, bromine at 2.96, and iodine at 2.66. This clear pattern allows us to predict relative electronegativity for any two elements just by knowing their positions in the periodic table. Electron affinity is the energy released when a neutral atom in the gaseous state captures an electron to form a negative ion. The general reaction is X gas plus an electron produces X minus gas plus energy. Chlorine has the highest known electron affinity at 349 kilojoules per mole. It releases the most energy because the added electron completes the 3p subshell, achieving the stable noble gas configuration of argon. Interestingly, fluorine has a slightly lower electron affinity of 328 kilojoules per mole, despite having higher electronegativity. This is because fluorine's compact 2p subshell causes significant electron-electron repulsion when adding an extra electron. This chart compares electron affinities across selected elements. Chlorine leads with 349 kilojoules per mole, followed by fluorine at 328, bromine at 325, and iodine at 295. Oxygen has 141, carbon 122, and hydrogen 73. Notice that nitrogen has a negative electron affinity of -7 kilojoules per mole. This means energy must be input to force electron capture due to its stable half-filled 2p subshell. The halogens clearly dominate the chart, while noble gases have negative electron affinities and do not form stable anions. Although electronegativity and electron affinity are related, they describe different phenomena. Electronegativity is a relative measure of how strongly an atom attracts shared electrons within a chemical bond. It is a property of an atom in a molecule. Electron affinity, on the other hand, is an absolute energy measurement for an isolated atom in the gas phase gaining an electron. Both quantities increase from left to right across the periodic table. However, electronegativity decreases down a group, while electron affinity does not always follow this trend. Chlorine has a higher electron affinity than fluorine, despite being lower in the group, because electron affinity is more sensitive to atomic size and electron-electron repulsion. This side-by-side comparison highlights the key differences and relationships between electronegativity and electron affinity. On the left, electronegativity is about attracting shared electrons in a bond, measured using the Pauling or Mulliken method, and it decreases down groups. On the right, electron affinity is about energy released when a neutral atom captures an electron, measured in kilojoules per mole, and it shows irregular trends down groups. The key relationship is that elements with high electronegativity tend to have high electron affinity, and both increase from left to right across the periodic table. But exceptions, like noble gases with low electron affinity, remind us these are distinct properties. Quiz question 1. Which element has the highest Pauling electronegativity value? Is it A, oxygen, B, chlorine, C, fluorine, or D, nitrogen? Take a moment to think about this. The correct answer is C, fluorine. Fluorine has the highest Pauling electronegativity at 3.98. It is the most electronegative element because it has the smallest atomic radius among the highly electronegative elements and the highest effective nuclear charge in its period. Quiz question 2. What is the electronegativity difference threshold above which a bond is considered predominantly ionic? Is it A, delta chi greater than 0.4, B, delta chi greater than 1.7, C, delta chi greater than 2.5, or D, delta chi greater than 3.0? The correct answer is B, delta chi greater than 1.7. A bond is considered predominantly ionic when the electronegativity difference exceeds 1.7 on the Pauling scale. Quiz question 3. Which element has the highest electron affinity? Is it A, fluorine, B, oxygen, C, chlorine, or D, bromine? The correct answer is C, chlorine. Chlorine has the highest electron affinity at 349 kilojoules per mole. When chlorine gains an electron, it achieves the stable electron configuration of argon. Quiz question 4. How is Mulliken electronegativity calculated? Is it A, from bond dissociation energies, B, as the geometric mean of atomic radius and nuclear charge, C, as the arithmetic mean of ionization energy and electron affinity, or D, from the covalent radius and effective nuclear charge? The correct answer is C. Mulliken electronegativity is the arithmetic mean of the first ionization energy and the electron affinity. It is called absolute electronegativity because it is based on fundamental atomic properties. Quiz question 5. In the water molecule, the oxygen atom has a partial negative charge, and the hydrogen atoms have partial positive charges. This is because A, oxygen has a higher electronegativity than hydrogen. B, hydrogen has a higher electronegativity than oxygen. C, both atoms have equal electronegativity. Or D, the bond is purely ionic. The correct answer is A. Oxygen has an electronegativity of 3.44, while hydrogen has 2.20. The difference of 1.24 makes the OH bonds polar covalent, with oxygen attracting electrons more strongly. Problem 1. Determining bond type from electronegativity differences. Given the Pauling electronegativities for oxygen, hydrogen, sodium, chlorine, carbon, and sulfur, calculate the electronegativity difference and classify the bond type for three cases: oxygen, hydrogen, sodium, chlorine, and carbon, sulfur. Follow along with the steps as they appear on screen. For oxygen-hydrogen, the difference is 1.24, which is a polar covalent bond. For sodium-chlorine, the difference is 2.23, which is an ionic bond. For carbon-sulfur, the difference is only 0.03, which is a nonpolar covalent bond. Problem 2. Mulliken electronegativity calculation. For chlorine, the ionization energy is 13.0 electron volts and the electron affinity is 3.62 electron volts. First, calculate the Mulliken absolute electronegativity. Then convert it to Pauling units using the formula. The Mulliken electronegativity is the average of 13.0 and 3.62, which gives 8.31 electron volts. To convert to Pauling units, we use the formula chi equals 0.187 times 16.62 plus 0.17, giving 3.28. This is very close to the literature value of 3.16. Problem 3. Electronegativity and bond ionization. The percent ionic character of a bond can be estimated using a formula. Calculate the percent ionic character for hydrogen fluoride and hydrogen chloride. Then explain why hydrogen fluoride is less ionic than expected from the electronegativity difference alone. For hydrogen fluoride, the ionic character is 43%. For hydrogen chloride, it is 18.6%. Hydrogen fluoride has significant covalent character, despite the high electronegativity difference, because fluorine's small size allows excellent orbital overlap. Problem 4. Electron affinity energy comparison. Given electron affinity values for chlorine, fluorine, oxygen, and nitrogen, calculate the energy released when 1 mole of chlorine atoms each gain 1 electron. Then explain why nitrogen has a negative electron affinity, and compare fluorine and chlorine in terms of their electron affinity values. 1 mole of chlorine atoms releases 349 kilojoules of energy. Nitrogen has a half-filled 2p subshell, which is very stable, so adding an electron is energetically unfavorable. Chlorine has higher electron affinity than fluorine because its larger 3p orbital has less electron repulsion. Problem 5. Predicting relative electronegativity without a table. For each pair, predict which element has the higher electronegativity and explain your reasoning. The pairs are sodium or magnesium, oxygen or sulfur, silicon or chlorine, and beryllium or boron. Magnesium has higher electronegativity than sodium because it is further right in period 3. Oxygen has higher electronegativity than sulfur because it is above sulfur in group 16. Chlorine has higher electronegativity than silicon because it is further right in period 3. Boron has higher electronegativity than beryllium because it is further right in period 2. Let us review the key concepts and formulas. Pauling electronegativity is based on bond dissociation energies. Fluorine is the most electronegative at 3.98 and cesium the least at 0.79. Mulliken electronegativity is the average of ionization energy and electron affinity. Bond polarity is determined by the electronegativity difference. Nonpolar covalent below 0.4, polar covalent between 0.4 and 1.7, and ionic above 1.7. Electronegativity increases left to right and decreases top to bottom in the periodic table. Electron affinity measures energy released when a neutral atom captures an electron. Chlorine has the highest value at 349 kilojoules per mole. Together, these concepts provide the fundamental framework for understanding chemical bonding. In conclusion, electronegativity and electron affinity are among the most powerful predictive tools in chemistry. From predicting whether a bond is ionic or covalent, to understanding why water is a polar molecule, to explaining why chlorine forms stable negative ions while nitrogen does not. These concepts permeate every branch of chemical science. The Pauling scale, now nearly a century old, remains one of the most frequently referenced chemical scales. The Mulliken scale connects these ideas to fundamental atomic properties. Together, they give us a quantitative understanding of how atoms interact, how molecules form, and how the properties of matter emerge from the behavior of electrons. Master these concepts and you unlock the language of chemical